And now in this lecture we'll answer on two questions. In the first question, we find out the area of this circle that is described by this trapezoid ABCD. And in the second question, we find out the length of this line segment QB that is equal to x. So we start with the first question. In the drawing, we have trapezoid ABCD that blocks this circle. This circle is inscribed by trapezoid ABCD. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment AB that is equal to B units in its length. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. And we define the point of tendency of this tangent AD with this circle. This point is point P. We define the point of tendency of this tangent BC with this circle. This point is point Q. Here we can implement rule 2. So I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extreme point to a circle are equal. In the drawing we have a circle, and this is the common extreme point, point P. From this common extreme point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if you focus on this common extreme point, point A, from this common extreme point, point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM is there, therefore AP must be also equal to A units in its length. Likewise, we focus on this common extreme point, point D. From this common extreme point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM equals to B units in its length, according to what is given in the question. Therefore, BQ must be also equal to each other, according to B, according to rule 2. BQ must be also equal to B units in itself, according to rule 2. So BQ equals to B units in itself, according to rule 2. In the next step, we join points O and Q together by straight line. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of this circle, and then at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, so we define the radius of this circle as x. Therefore, OQ equals to x units. Itself, it is the radius of this circle. And because of the fact that the radius OQ that is equal to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle that is equal to x, and because of the fact that the radius OP that is equal to x, the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever we have radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. The next step, we will do a construction. That is to say, from this point, point A, we will draw perpendicular on BC. Again, from point A, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BC. This point is point N. By doing this construction, we're going to do those two angles. Those two angles are defined as one-sided interior angles, and are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid, and the definition of a trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. So those two angles are both defined as one-sided interior angles, and they are located between the parallels AD and BC, and therefore according to rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. So I repeat quickly on rule 17. According to rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B, and this is line, the red line C intersects with those two parallel lines A and B and those 2 points. In addition, we have those two angles alpha and beta that are defined as one-sided interior angles. And because of the fact that those two angles alpha and beta that are defined as one-sided interior angles are located between the parallel lines A and B, therefore the sum of those two one-sided interior angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. As I already mentioned before, we have implemented rule 17 in our drawing. We already implemented rule 17 in our drawing. Why? Because in our drawing, those two angles are defined as one-sided interior angles, and they are located between the parallel lines AD and BC. And therefore, according to rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. But this angle equals to 90 degrees according to our construction. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say, from this point O, we will do perpendicular on AN. Again, from point O, we will do perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created the small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. Likewise, inside the lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle, in total They must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 450 angle must be equal to 90 degrees in its sides. So if we found out that the big angle POQ, this is the big angle POQ equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle POQ is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is a straight line. So line segment POQ is a straight line. If line segment POQ is a straight line, PQ is also a straight line. PQ is a straight line. Line segment PQ is a straight line. So PQ is a straight line. So in shape APQN, in this shape APQN or shape APQN consists of 4 sides. 1, 2, 3, 4. Okay, shape APQN consists of 4 sides. And therefore, shape APQN is a quadrilateral. Shape APQN is a quadrilateral. But we've already found out that quadrilateral APQN consists of 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. So I write it down. Quadrilateral APQN, the big quadrilateral APQN is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle APQN, side AB must be equal to the opposite side NQ. But AP is 8, therefore NQ must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x, so therefore AN must be, the opposite side AN must be also equal to 2x units in its length. So this is side AN, the opposite side AN, that is, must be also equal to 2x units in its length. What is the length of this missing line segment BN? From the drawing it is very easy to see that BN in total equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So I write it down. BN equals to BQ minus NQ. So in total BN equals to BQ. BQ is B according to rule 2. Minus NQ. NQ is A. So in total, BN equals to B minus A units in its length. This small line segment BN is B minus A units. So, in the next step, and copy the right triangle triangle A and B in a new page, and we implement the Pythagoras theorem on this right triangle triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AN equals to 2x units in its length, side BN equals to B minus A units in its length, and the hypotenuse AB equals to A plus B units in its length. Here by PT is the proportion for Pythagoras theorem. So actually, this is the right triangle ABN that are coming from the original drawing, and this right triangle ABN, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. So I'll write it down. AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared, 2x squared is 4x squared, plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So total we found out that A plus B squared equals to 4x squared plus B minus A squared. We'll open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. So here we have A squared on both sides of this equation, so A squared will get cancelled. And we also have B squared on both sides of this equation, so B squared also gets cancelled. After we cancel those two expressions, in this side of the equation we left only with 2AB. On the other side of the equation we left with 4x squared minus 2AB. So here we add 2AB to this equation, and we get that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. And again, we found out that 4x squared equals to 4AB. Here we divide this equation by 4. And we get that 4AB over 4 is AB, and 4x squared over 4 is x squared. So in total we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle must be equal to pi times x squared. But we have already found out that x squared equals to AB. Therefore, we substitute x squared here by AB, and you get that the area of the circle is equal to pi times x squared, and x squared is AB, so it is pi times AB square units in its length. Repeat again. We actually found out that the area of the circle, that is the area that we are looking for this question, is equal to pi times AB square units. That is the answer to the question. So finish with the first question. In the next step, I will present to you the second question and we'll solve the second question of this lecture. Our mission in this second question is to find out the length of this isosceles cubit is equal to x. We have to find out the value of x. So in the drawing, we have this semicircle. Inside this semicircle, we have this chord AP that is equal to 10 units in itself. This is chord PQ that is also equal to 10 units in itself. This is AB. AB is the diameter of this semicircle that is equal to 30 units in its length. And finally, this is chord QB that is equal to x units in itself. So our mission is to find out the length of chord QB that is equal to x units in itself. So we have to find out the value of x. So in the first step, we will define the center of this semicircle. This point is point O. It is given as a question that the diameter of this semicircle AB is 30 units. If the diameter is 30 units, the radius must be equal to half of it. So the radius is 30 over 2, that is 15. Point O is the center of this semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to 15 units. OB is also the radius of this semicircle, that is equal to 15 units in its length. In the next step, we will join points O and P together by straight line. Point O is the center of this semicircle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle that is equal to 15 units in its length. In the next step, we will complete this semicircle to a circle. And we'll extend the radius PO on this semicircle by a straight line until it touches the circle. Actually, this is the touching point of the extended radius PO with this circle, so we'll define this touching point as point M. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle that is equal to 15 units in its length. In the next step, we will join points M and B together by a straight line. Those two angles, they are defined as vertex angles, so we know that vertex angles are equal to each other. So this is angle theta, that this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. In the next step, I will prove that triangle APO can go into this triangle MOB. So we have to prove that triangle AOP can go into triangle OMB. So why those two triangles can go into each other? First of all, side OP in triangle AOP is equal to side OM in this triangle OMB. They're both the radius of the circle that is equal to 15 units in its length, therefore they are equal to each other. So I write it down. AP equals to OM. Above the radius of the circle that is equal to 15 units in its length, therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and vertex angles are equal to each other. This is angle AOP in triangle AOP. And it is equal to this angle, this is actually angle MOB in triangle OMB. Are equal to each other according to the rule that vertex angles are equal to each other. And finally, side AO in triangle AOP is equal to side OB in triangle OMB. They are both the radius of the circle that is equal to 15 units in its length, and therefore they are equal to each other. AO equals to OB equals to 15. Again, side AO equals to side OB equals to 15 units in its length. They are both the radius of the circle, therefore they are equal to each other. So we actually proved that those two sides and the angle that is included between those two sides in triangle AOP are correspondingly equal to those two sides and the angle that is included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. So right now we shall prove that triangle AOP congruent, this is the sign of congruent, to triangle OMB according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that side AP equals to side MB. AP equals to MB. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AB and MB, must be also equal to each other. But AP equals to 10 units in its length, according to what is given as the question. So we can write here that AP equals to 10. And for this equation, 10 equals to AP equals to MB. We derive that MB is also equals to 10 units in its length. MB equals to 10. MB equals to 10. Chord PM passes through point O, that is the center of the circle. We know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PM is the diameter of the circle. So I'll copy this semicircle with the diameter PM, and we analyze this semicircle with the diameter PM. So here, this is the semicircle with the diameter PM that I copied from this drawing, from the original drawing. So we have here, point O is the center of this circle, PM is the diameter of the semicircle, and also the diameter of the circle. PQ equals to 10 units in its length, MB also equals to 10 units in its length, and QB is the missing line segment, the line segment that we are looking for in this question. We have to find out the length of QB is equal to X. So we know that line segment PQ equals to line segment MB. They are both equal to 10 units in their length, therefore they are equal to each other. So we'll extend line segment PQ by side line and line segment MB by side line until they touch each other. So this is the touching point. So we define the touching point, this point is point E. Again, PQ equals to MB. When you extend two line segments that are equal to each other in their lengths until they intersect with each other, the line segments that will add it to the original line segment must be equal to each other. That is to say, BE equals to QE. Again, when you extend two line segments that are equal to each other in their lengths by side line until they intersect with each other, the extended line segments must be also equal to each other. That is to say, BE equals to QE. So we define BE as Y. If BE is Y, then QE must be also equal to Y. So in total, side PE equals to ten plus Y, and side EM also equals to 10 plus Y. And from this equation, PE equals to 10 plus Y equals to EM, we derive that PE equals to EM. So in triangle MEP, side EP equals to side EM. This is triangle EPM. And we know that in triangle EPM, side EP equals to side EM, therefore this triangle EPM is an isosceles triangle. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side EP we have this angle that is angle PME, and in front of this side EM we have this angle that is angle MPE. And because of the fact that those two angles are located between those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta according to the rule that I mentioned. Okay. So in the next step, we'll complete the semicircle to a circle. So we have here a circle, and this is quadrilateral PQBM that is inscribed by this circle. Again, this is quadrilateral PQBM that is inscribed by this circle. And we have the rule that says that any quadrilateral that is inscribed by a circle, its two opposite angles must be equal to, the sum of its two opposite angles must be equal to 180 degrees. Because of the fact that quadrilateral PMPQ is described by this circle, the sum of its two opposite angles must be equal to 180 degrees. Those are the two opposite angles of this quadrilateral QBMP, therefore the sum of those two opposite angles must be equal to 180 degrees. This is angle beta plus this missing angle in total must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is equal to 180 degrees. That is the sum of the angles, the sum of the opposite angles in a quadrilateral that is described by a circle. So this angle must be equal to 180 degrees minus beta. Likewise, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, so this is angle beta plus this is missing angle in total must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles, the sum of the opposite angles in a quadrilateral that is described by a circle. So those two angles, the sum of those two angles is 180 degrees, because 180 degrees minus beta plus beta is 180 degrees. But those two angles are defined as one-sided interior angles, and whenever you have one-sided interior angles that the sum of them is 180 degrees, they must be located between parallel lines. Therefore, line QB is parallel to line PM according to rule 18. So I repeat quickly on rule 18. According to rule 18, if the sum of two one-sided triangles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing, we have line A and line B. This is line C that intersects with those two lines A and B at those 2 points. Those are angles alpha and beta that are defined as one-sided interior angles. And we know that the sum of those two angles alpha and beta is equal to 180 degrees. And therefore, because of the fact that the sum of those two one-sided interior angles is equal to 180 degrees, they must be located between parallel lines. That is to say, line A is parallel to line B. So we can implement rule 18 in our drawing. Why? Because in our drawing, those two angles are defined as one-sided interior angles, and the sum of those two angles is 180 degrees. Therefore, according to rule 18, they must be located between two parallel lines. That is to say, QB is parallel to PM. So it is known. We actually found out that according to rule 18, QB is parallel to PM. QB is parallel to PM. Okay. So in the next step, I will copy again this semicircle with the diameter PM. In a new page, we continue to analyze this semicircle with the diameter PM. Okay, this is the semicircle with the diameter PM. The point from the original domain. Here we have point O is the center of the circle, point P is the point of the semicircle itself, therefore P is the radius of the semicircle, that is 15. Likewise, OM is also the radius of the semicircle, that is also 15. We join points O and Q together by a straight line. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the semicircle, and ends at point Q, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of the semicircle, that is equal to 15 units in its length. Likewise, we join points O and B together by a straight line. OB is also the radius of the semicircle, that is equal to 15 units in its length. According to Rule 18, QB is parallel to PM. Okay, QB is parallel to PM. So those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. And therefore, according to Rule 15, they are equal to each other. So repeat quickly on Rule 15. According to Rule 15, alternating angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B. This is line C that intersects with those two parallel lines at those 2 points. Those are angles alpha and beta that are defined as alternating angles, and because of the fact that those two alternating angles are located between the 2 parallel lines A and B, they must be equal to each other in their sizes. This is why alpha equals to beta. So we can actually implement Rule 15 in our drawing. Why? Because of the fact that those two angles are defined as alternating angles, and they are located between the 2 parallel lines QB and PM. Therefore, they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. So I will implement the law of cosines in this green triangle QOP, and in this white triangle QOB. So I will present to you the law of cosines quickly, and we'll implement the law of cosines on those 2 triangles. So actually, the law of cosines is through an N triangle. So actually, this is triangle ABC that could be any triangle. This is side AB that is equal to A units in its length. This is side AC that is equal to B units in its length. And this is side BC, it is equal to C units in its length. This is angle theta. According to the law of cosines, This triangle ABC, cosine theta is equal to A squared plus B squared minus C squared divided by 2 times A times B. Repeat again. In this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So, in the next step, I'll copy the green triangle PQO in the page, and we will implement the law of cosines in this green triangle PQO. Side PQ equals to 10 units in length. Side PO equals to 15 units in length. This is the radius of the semicircle. Side OQ also equals to 15 units in length. And this is angle alpha. So hopefully this is triangle PQ, the green triangle PQO that I copied from this drawing. And in the next step, we will implement the law of cosines in this triangle PQO. According to the law of cosines, this triangle PQO this will be equation 1. Cosine alpha is equal to 15 squared plus 15 squared minus 10 squared divided by 2 times 15 times 15. But again, cosine alpha in this triangle PQA is equal to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. In the next step, I copy triangle QOB, and in the present we will implement the law of cosines in the triangle QOB. So here, this is triangle QOB that is coming from this drawing. This triangle QOB, according to the law of cosines, this will be equation 2. Cosine alpha equals to x squared plus 15 squared minus 15 squared divided by 2 times x times 15. Repeat again, this triangle OQB according to the law of cosines. Cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for cosine alpha. So in the next step we create equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 equals to 15 squared plus 15 squared minus 10 squared divided by 2 times 15 times 15. So this is cosine alpha according to equation 1, and cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 is equal to x squared plus 15 squared minus 15 squared divided by 2 times x times 15. So if we focus on the denominator of these expressions, we have 2 times 15 on both denominators, so 2 times 15 will get cancelled. In this side of the equation we have 15 squared minus 15 squared, that is 0. So those two expressions will get cancelled. So in this side of the equation we left only with x squared over x. X squared over x is x. So if you found out that x equals to, here we have 15 squared plus 15 squared minus 10 squared divided by 15. So if we found out that x equals to, according to equation 3, x equals to 15 squared is 225, so 225 plus 225 is 450 minus 10 squared. 10 squared is 100, so it is minus 100 over 15. So total if we found out that according to equation 3, x equals to 450 minus 100 is 350 over 15. So total if we found out that according to equation 3, x equals to 350 over 15. So here we will divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70, and 15 over 5 is 3. So in total if we found out that x 9/7 cubic is equal to x, it is equal to either 70 over 3 units in its length, or 70 over 3 is 23 and third units in its length, and that is the answer to the second question. I repeat again that we found out that the length of this line segment QB is equal to x, is equal to either 70 over 3 units in itself, or QB is equal to x is equal to 23 and 3 units in itself. So finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this circle that is described by this trapezoid ABCD. So in the drawing, we have trapezoid ABCD that blocks this circle, or the circle is described by trapezoid ABCD. In addition, we know that this is line segment AM that is equal to units in itself. This is line segment A and B that is equal to B units in itself. Again, our mission is to find out the area of this circle that is described by trapezoid ABCD. So first of all, we defined the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. We define the point of tendency of tangent BC with this circle. This point is point Q. Here we implemented rule 2. If we focus on this convex point, point A, from this convex point, point A, we have two tangents to this circle, tangent AP and tangent AM, and according to rule 2, they are equal to each other. That is to say, AM equals to AP, but AM is A, therefore AP must be also equal to units in itself. Likewise, if we focus on this convex point, point B. From this convex point, point B, we have two tangents to this circle, tangent BQ and tangent BM, and according to rule 2, they are equal to each other. This is to say BM equals to BQ, but BQ equals to B units in itself, according to what is given in the question. Therefore, BQ must be also equal to B units in itself, according to rule 2. In the next step, we did the construction, that is to say, from this point A, we do perpendicular on BC. Again, from point A, we do perpendicular on BC. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. We know that in the trapezoid ABCD, side AD is parallel to side BC. By doing this construction, we're going to do those two angles. Those two angles are defined as one-sided interangles, and they are located between the parallel lines AD and BC. And therefore, the sum of those two angles must be equal to 180 degrees according to rule 17. But this angle equals to 90 degrees according to our construction. So 90 degrees plus BC angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this BC angle must be equal to 90 degrees in its size. In the next step, we did another construction, that is to say, from this point O, we drew perpendicular on AN. Again, from point O, we drew perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. When doing this construction, we created the small quadrilateral APOT. Beside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in its size. Likewise, if you focus on this small quadrilateral TOQN, inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 470 degrees, so 270 70 degrees plus the size of this 4 missing again, total must be equal to 360 degrees. Therefore, this 4 missing again must be equal to 90 degrees in its size. So the big angle POQ equals to 90 degrees plus 90 degrees, that is 180 degrees. The big angle POQ equals to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size must be a straight line. So line segment POQ is a straight line. Line segment POQ is a straight line. If line segment POQ is a straight line, then PQ is also a straight line. PQ is a straight line. And so in shape APQN, in this shape APQN, we have 4 sides. 1, 2, 3, 4, and therefore, again, in shape APQN, we have 4 sides, and therefore, shape APQN is a quadrilateral. Okay, because it has 4 sides, but in quadrilateral APQN we have 4 right angles, and according to Rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle APQN, side AP must be equal to the opposite side QN. But AP is A, therefore QN must be also equal to N in itself. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to X plus X, that is 2X. Therefore, AN must be also equal to 2X units in itself. What is the length of this missing line segment BN? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ, that is B, minus NQ, that is A. So in total, BN equals to B minus A units in itself. In the next step, I copy the right triangle A and B in the new page and implemented the Pythagoras theorem with this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle A and B, that according to the original domain. Side AB equals to A plus B units, side AN equals to 2X, and side BN equals to B minus A units in itself. So this triangle, the right triangle ABN, AB square equals to AN square plus BN square. AB is A plus B, therefore AB square is A plus B square, and it is equal to AN square. AN is 2X, therefore AN square is 2X squared, that is 4X square, plus BN square. BN is B minus A, therefore BN square is B minus A square. So in total, we actually found out that A plus B square equals to actually found out that AB square equals to A square plus BN square. AB square is A plus B square. This equals to 4X square plus B minus A square. We open the brackets on both sides of this equation and finally found out that A plus B square equals to A square plus B square plus 2AB. And it is equals to 4X square plus B minus A square. B minus A square equals to B square plus A square minus 2 times A times B. Here we have A square on both sides of this equation, so A square will get cancelled. And we also have B square on both sides of this equation. So B square also will get cancelled. After we cancel those two expressions, this side of the equation we left only with 2AB, and the other side of this equation, this side we left only with 4X square minus 2AB. So in total we found out that 2AB equals to 4X square minus 2AB. Here we added 2AB to this equation, and finally found out that 2AB plus 2AB is 4AB, so 4AB equals to 4X square. Here we divided this equation by 4 and finally found out that 4AB over 4 is AB and 4X square over 4 is X square. So in total we found out that X square equals to AB. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle must be equal to pi x squared. But x squared is AB. According to this equation, x squared is AB. So we solve x squared here by AB. And finally found out that the area of this circle, that is the area that we are looking for in this question, is equal to pi times AB square units. Again, the area of this circle is equal to pi times AB square units. We finished with the first question. So in the next step, I presented to you the second question, and we solved the second question of this lecture. second question, our mission is to find out the length of this line segment qubit is equal to x. We have to find out the value of x. So in the original domain we have a semicircle, and inside this semicircle we have this is called AP, that is equal to 10 units in its length. This is called PQ, that is also equal to 10 units in its length. This is line segment qubit, that is equal to x. And our mission is to find out the length of this line segment qubit is equal to x. We have to find out the value of x. In addition, we know that this is line segment AB. AB actually it is the diameter of this semicircle that is equal to 30 units in its length. Again, our mission is to find out the length of this line segment qubit is equal to x. So, in the first step, we define the center of this semicircle. This point is point O. And the diameter of this semicircle is 30, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. Point O is the center of the circle, point A is the point of the circle itself, therefore always the radius of the circle is equal to 15. Likewise, OB is also the radius of the circle that is equal to 15. We join points O and P together by side line. OP is also the radius of this circle that is 15. In the next step, we completed this semicircle to a circle, and we extended side PO until the radius PO until it touches the circle at this point. This is the touching point of the extended radius PO with the circle. We define their touching point. This point is point M. And here we have we join points M and B together by sub line. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to each other, because they are equal to each other according to the rule that I mentioned. In the next step, we prove that this triangle APO is congruent to this triangle MOB. So why those two triangles congruent to each other? First of all, side PO equals to side OM, they're both the radius of the circle, therefore they are equal to each other. In addition, those two angles are vertex angles, and we know that vertex angles are equal to each other. And finally, side AO of triangle APO is equal to side OB of triangle OBM. They are both the radius of the circle, and therefore they are equal to each other. So I shall prove that those two sides and the angle that is included between those two sides in triangle APO correspondingly equal to those two sides and the angle that is included between those two sides in triangle MOB. Therefore, those two triangles can join to each other according to angle side rule. And from the fact that they can join to each other, we derive that side AP is equal to side AB according to the rule that corresponding angles and corresponding sides in congruent triangles are equal to each other. Those two triangles can join to each other, and therefore those two corresponding sides AP and B must be also equal to each other. And again, AP equals to MB. But we know that AP equals to 10 units in its length according to what is given in the question. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we derive that MB equals to 10 units in its length. This is side MB, this is equal to 10 units in its length. Chord PM passes from point O, that is the center of this semicircle, and we know that any chord that passes from the center of the semicircle of a circle is the diameter of this semicircle. So PM is the diameter of this semicircle. So copy the semicircle with the diameter PM, and in the plate we analyze this semicircle. Okay, this is the semicircle with the diameter of PM, which is coming from the original drawing. Line segment PQ equals to line segment MB equals to 10 units in its length. We actually extended side PQ and side MB, or line segment PQ and line segment MB by side line until they touch each other at this point. This is point 8, this is their touching point. Actually, when we extend two line segments that are equal to each other in their lengths, then until they intersect with each other, then this QE will be equal to BE. Okay? When you extend two line segments that are equal to each other, then what you added here, QE, must be equal to BE. So if QE is Y, then BE must be also equal to Y. So in total, AE equals to 10 plus Y from one side, but we also know that ME also equals to 10 plus Y. And therefore, PE is equal to EM. In triangle PEM, side PE equals to side EM, and therefore triangle PEM is an isosceles triangle, and we know that in front of equal sides in the triangle there are equal angles. So actually in front of this side PE we have this angle, and in front of this side EM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle, the size of this angle must be also equal to beta according to the rule that I mentioned. Okay, so those two angles are equal to beta. And in the next step, I completed this semicircle to a circle. Actually, we have here quadrilateral PQBM is inscribed by this circle. And we have the rule that states that any quadrilateral that is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. And because of the fact that this quadrilateral PQBM is inscribed by this circle, the sum of its two opposite angles must be equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees. But this is angle beta. So angle beta plus the size of this missing angle in total must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles of the opposite sides. The sum of the opposite sides, the sum of the opposite angles in a quadrilateral that is described by a circle. So this missing angle must be equal to 180 degrees minus beta. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. So this is angle beta, therefore this missing angle must be equal to 180 degrees minus beta, exactly because of the same reason that this angle equals to 180 degrees minus beta. So in total we found out that those two angles, the sum of those two angles is 180 degrees. Why? Because 180 degrees minus beta plus beta is 180 degrees. So those two angles are defined as one-sided interior angles, and we know that the sum of those two angles is equal to 180 degrees. And according to rule 18, if the sum of two one-sided interior angles is equal to 180 degrees, then they must be located between parallel lines. That is to say, according to rule 18, line QB must be parallel to line PM. QB is parallel to line PM according to rule 18. In the next step, I copied the semicircle with the diameter PM, and in Euclid we continue to analyze this semicircle. So actually, this is the semicircle with the diameter PM that I copied from the original drawing. PQ equals to 10 units in itself, and B also equals to 10 units in itself. QB is the missing line segment that we are looking for in this question. We join points Q and O together, O and Q together by straight line. OQ is the radius of the semicircle that is 15. We join points O and B together by straight line. OB is also the radius of the semicircle that is 15. OP is the radius that is 15. OM is also the radius that is 15. According to rule 18, side QB is parallel to side PM. And again, QB is parallel to PM. So those two angles, they are defined as alternating angles. and they are located between the parallel lines QB and PM. And according to rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles must be equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be equal to alpha according to rule 15. So in the next step, I presented to you the law of cosines, and we presented the law of cosines in this right triangle QPO, and in this right triangle QOB. So according to the law of cosines is true in any triangle. This is triangle ABC that it could be any triangle. This triangle ABC, the law for side AB is A unit, side AC equals to B units in itself, and side BC equals to C units in itself. This is angle theta. According to the law of cosines, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, I copied this grand triangle QOP in a new page and implemented the law of cosines in this grand triangle, triangle QOP. So actually, this is the grand triangle QOP that I copied from the original drawing. QP equals to 10 units in itself, OQ is 15, and PO is also 15. This is angle alpha. According to the law of cosines, in this triangle QPO, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. Again, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. Okay, this is equation 1. In the next step, I copied this triangle QOB in a page and implemented the law of cosines in this triangle, triangle QOB. Actually, this is triangle QOB that I copied from the original drawing, and this triangle QOB, OQ equals to 15, OB also equals to 15, they are both the radii of the circle, or the semicircle that is equals to 15. QB is the missing line segment that we are looking for in this question, and this is angle alpha. This triangle QOB, according to the law of cosines, cosine alpha, this is equation 2, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Again, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for cosine alpha. Equation 1, this is equation 2. In the next step, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 is 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Again, this equation means that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So if we focus on the denominator of those two expressions, in both the denominators we have 2 and 15, so 2 and 15 will get cancelled. And in this side of the equation, we have 15 squared minus 15 squared, that is 0. So in total we left in this side of the equation only with x squared over x, that is x. In the other side of this equation we left with 15 squared plus 15 squared minus 10 squared over 15, because 2 and 15 will get cancelled. So in total we have found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. 15 squared is 225, so 225 plus 225 is 450, minus 10 squared. Minus 10 squared is minus 100, so we have 450 minus 100 over 15. 450 minus 100 is 350. So in total we have found out that x equals to 350 over 15. Here we divided both the numerator and the denominator of this number by 5 and found out actually that 350 over 5 is 70 and 15 over 5 is 3. So in total we found out that q bit is equal to x. It is equal to either 70 over 3 units in its term, and also numbers, it is equal to 23 and third units in its term. I'll repeat again. We found out that the length of this line segment q bit is equal to x. It is equal to either 70 over 3 units, in terms of numbers, the length of this line segment q bit is equal to x is equal to 23 and third units in its term. Okay? Thank you very much.